Section 14.5 is about the chain rule, which we can expect is going to be a way of taking the derivative of function compositions. But what's kind of neat is we've got all these nifty new sorts of functions to work with. So in chapter 13, I've got this labeled, by the way, as case 1. The book breaks the chain rule up into 2 cases, and this is case 1. We'll do case 2 later. Okay. So in chapter 13, we worked with functions like this, where our input was one-dimensional, but our output was multidimensional. So we'd have a vector function. Now, I've written it with the domain being all of R. Of course, for some vector functions, we've seen that we would need to replace that with the domain, which would be some subset of R. I'm just writing it right now with the domain being all of R so that we can really clearly see that this is a one-dimensional input that we're then mapping to a multi-dimensional output. Our output would be a vector in n space, and of course we associate that vector with a point. We think of this as the position vector for a point in n space. And then in chapter 14, we've been studying functions where the domain is multidimensional. And again, I wrote this one as if the domain is all of Rn. That's often the case, but if it's not, we would just replace this right here with whatever the domain was, which would be some subset of Rn. And we've been looking at functions that map us to real numbers, so that the codomain is one-dimensional. Well, if this n and this n are the same, then I could compose these functions. Let's just give ourselves a specific example here. Let's suppose that R was mapping from the real numbers to 2 space, and it took a value t, and it mapped it to t squared e to the t. Okay, fabulous. That, of course, is giving me x as a function of t and y as a function of t. And then let's suppose that f was mapping from 2 space to the real numbers, and it was taking a point xy, and it was mapping it to, let's go to xy squared. Okay, well, I could compose these functions. Okay, I'm going to look at this particular order, looking at f of r of t. A composition will be defined if the output of one function is in the domain of the second function. So the output from r of t was going to be a point in 2 space. That's in the domain of f, so I can do this. We could actually compose these particular functions in the opposite order. I could map a point in the real numbers to a single number, and then I could plug that into r, and I get out a different point in 2 space. That would be looking at a function that mapped us from 2 space to 2 space. We're going to look at that a little bit this semester. Most of the functions we work with, though, are going to either start in the real numbers or end in the real numbers. So we'll have either a domain or a codomain that's one-dimensional. Okay. All right. So if I look at f of r of t, okay, that's going to be a function that maps from r to r. It would map a t value to f of r of t. Okay. Now here I might be thinking of this as my z value for this particular function. Let's see what this function composition would look like. If I calculated f of r of t, that's just f of t squared e to the t. That's my x. That's my y. I'm supposed to plug in to get x times y squared. That would just be t squared times e to the 2t. Okay. So notice what I get is actually just a real valued function of one variable. That's the sort of thing where in 3a or 3b you could take the derivative of that without knowing anything about multivariable calculus, because we've created a function that starts in the real numbers and ends in the real numbers. Okay. So what's happened, I can sort of draw a diagram for this, is we started in the real numbers, we applied the function r to get to 2 space, and then we applied the function f to get back to the real numbers. So we took a t value to a point xy, and then we mapped that to our z value. Okay. Now, I could certainly just take the derivative of this using techniques from single variable calculus. Okay. But what I want to do is see if we can't use the chain rule for functions of more than one variable. Obviously, in taking the derivative of the e to the 2t part, I'd be using the chain rule for functions of one variable because that's a function composition. But I'd like to see if we can find a generalization of the chain rule. And that's because sometimes we're going to be concerned not just with the end result, this is the formula that I got, but with the process by which we built that thing. Okay. And the chain rule is going to allow us to find the derivative of the ultimate product here in terms of derivatives of the functions that we have along the way. So let's see if we can figure out how that works. What I'm going to do here is, let's see, I want to keep up that much. Okay, so the ultimate output is z. I'm going to create a diagram where I put the ultimate output on top, and I'm going to sort of work backwards. I got that output in terms of x and y. So I'm going to draw these bars here. This is saying there's a dependence relationship here. The value of z depends on x. The value of z also depends on y. Okay. Now, x and y, those were my component functions for this vector function r. So each of them, in turn, depended on t. So I'm going to say x depends on t and y depends on t. Now, that's actually the same t. Okay. I'm writing it twice rather than writing it once, just because as we start looking at some more complicated things, the diagram can get kind of complicated, and I'm trying to sort of keep things spaced out. It would be perfectly acceptable in this particular case to simply say they both depended on t. That actually shows t gives me x and y give me z. But I'm going to just be in the habit of sort of writing the input variable for each function separately below it and just rely on my common sense to say, hey, that's the same letter. That's really just one input variable. And you'll see why when we get to case 2, the diagram just gets really complicated if you don't do this. Okay, so this gives me a dependence relationship. The value of t influences the value of both x and y, which in turn influences the value of z. This diagram is just going to help me sort of keep track of things. Okay, so what I'm going to do now is along each one of these lines that's connecting variables, since that's giving me a dependence relationship, there's a derivative that measures the corresponding rate of change. Okay. So what derivative measures the rate of change between x and z? Well, since z has 2 variables that determine its value, I know that that's going to be a partial derivative rather than a full derivative. So this would just be the partial of z with respect to x. Okay. And here, the partial of z with respect to y would measure that relationship. And if I preferred, since the function that's giving me my z values is f, if I wanted to write the partial of f with respect to x and the partial of f with respect to y, that would be perfectly fine. Okay. All right. Then I'm going to look at these dependence relations. Okay. So here, there's only one line leading from x to a variable. X is a function of just one variable, so this is going to be a full rather than a partial derivative. I can just write that as x prime of t. Okay. Same thing here, y is a function of just one variable, So I can write that as y prime of t. You'll notice these are the two components of r prime of t, since x and y were the component functions of r. Okay. Now, what I'm ultimately trying to build here is the derivative of this variable with respect to what I have on the bottom. Now on the bottom, even though I've written it twice, I only have one variable. So if it's a function of one variable, we're talking about a full derivative, not a partial derivative. So I'm trying to find dz by dt. Now here, I don't have the option of writing f instead of z here, because f is only dealing with this part. F is the relationship between x and y and z. Okay, so I'm looking at dz by dt, or I could write it as the full derivative with respect to t. If I want to use the name f, I need to indicate that it's f of r of t, because f wasn't a function of t, f was a function of x and y. Okay, but if I want to find this, here's basically what I want to do. I can say z is connected to t two different ways. Okay, so this tells me how z is affected by t because t influences the value of x, which has an effect on z. This path tells me t affects y, which in turn affects z. Okay. What I'm going to do is I'm going to multiply the derivatives along each path. If we think about chain rule, we're used to multiplying derivatives together. But then I'm going to add them together because there are two ways in which t can influence my function f. So we're going to get the partial of z with respect to x times x prime of t plus the partial of z with respect to y times y prime of t. Okay, I need to clear myself a little bit more space, so I'm just going to copy the formulas that we're working with. R of t is t squared e to the t, and f of xy is xy squared. Okay, so now I can clear that up. Okay, excellent. So I basically just multiply derivatives along each path and then add together the products that I get along each path. Notice that's giving me a sum of products. When do I get a sum of products? When I'm taking a dot product. So if I wanted to, I could say, that's the partial of z with respect to x, comma, partial of z with respect to y, dotted with x prime of t, y prime of t. This is essentially just this dot product, okay, where I put the two partial derivatives that I got from the top part of my diagram into one vector and the two full derivatives from the bottom part down here. But what's really neat is what I'm actually dotting here are two derivatives. This is the gradient of f, right? Because that's the two partials of my function f, which was the function that was giving me z. And this is just r prime of t. So if I think about the chain rule and I say, oh yeah, you multiply the derivative of the outside part, evaluated at the inside part, you multiply that by the derivative of the inside part, all we're doing here is we're replacing multiplication with the dot product, which I think is pretty cool. Okay, not necessary to write it as this dot product. Very often I'm just going to write it out this way because I remember the formula by working with this diagram. What I do want to do is just work it out for this particular example. Okay, so let's see. I've got this formula to remind me. Let me just copy that up here. Partial z partial x times x prime of t plus partial z partial y times y prime of t. Generally what I'll do is I'll use the diagram to get the general formula, and then I'll plug in. So what is the partial of z with respect to x? Looks like that's going to be y squared. What is x prime of t? Well, this was my x function, so that's going to just be 2t. Plus, what was the partial of z with respect to y? Looks like that's going to be 2xy. What was the derivative of y with respect to t? If y was e to the t, that's just going to be e to the t. Now, this is an intermediate step here. I don't want that to be my final answer because right now I've got 3 variables in there. I'm explaining this in terms of x and y and t. The rule is I can only use the variables that I've got on the bottom level because we're ultimately saying that z is a function of just one variable t, so its derivative really should be in terms of just one variable t. Okay. So what I need to do then is simply express x and y in terms of what they are in terms of t. So basically taking advantage of the fact that that was a formula for x and that was a formula for y. Remember, we evaluate the derivative of the outside part. That's essentially what we're doing first here. We evaluate that at the inside part. So rather than writing x and y, I want to write x of t and y of t. So my y squared becomes e to the 2t. I'm multiplying that by 2t. I'm just going to write the 2t first so that it's super clear that that's not part of the exponent. Okay. Plus 2 times x times y, that's going to become 2 times x was t squared. Y is e to the t times another e to the t, that's going to become an e to the 2t. So this would be my final answer for the derivative of this particular function composition. Kind of cool. And earlier we did write out what this composition was as just a single function of t. If you want to, you can certainly confirm that just using the rules from single variable calculus, we would get the same thing. On exams and quizzes, if I just gave you this function composition, I said find the derivative, you can do it any way. But I'm not going to do that. I'm going to say find the derivative using the chain rule for functions of more than one variable, so that I would want you to do it this way. Because we'll see, particularly in the next section, that it's necessary to understand this process in order to develop some theory. Sometimes just working with the result isn't enough. You need to understand how a function was built in order to be able to fully work with it. And we'll see that when we get to section 14.6.